All right, so today we're going to talk about failure states in our Intro to Logic and Troubleshooting course. So here's a little outline of what we're going to talk about today. So we're going to talk about covert and overt failures, and basically how different failures present themselves. Then we're going to look at failure states and some example applications. So on the right-hand side here, I just have a simple circuit that I made using the circuit software listed right there, CIRKIT. And basically you can build these little circuits and test them out. So this one would just indicate, I have a running indicator here, green, so that's everything's good. And then basically I have some sort of fail indicator, the red light. This took me way too long to put together. Oops. So I thought it was just kind of fun to show it in here. All right, so this is just a review from the previous lecture. We're going to talk about technical failures. So just to remind us, a technical failure is when a system or a component is not achieving the desired state or does not complete the proper function. So everything fails. It's just a matter of knowing how and when, and it's our responsibility as engineers or as technicians to understand why failure occurs. And here, when I say the why, I mean the root cause of the failure. So how mechanical failures present themselves. So there's overt failures and covert failures. The overt failure is something that's self-revealing, easily identifiable, or directly informed. So you either get the information from a gauge, a digital readout, or something like that. Now this could also include physical changes in the system. So if you smell something, if you see smoke, if you hear a big or a thud or a big crash or something that's not normally part of the system, this indicates that something went wrong. So continuous control systems are things that are operated continuously. They have components that are constantly monitored. In your car when you have it running, your temperature and your pressure inside the car are monitored at certain locations, typically corresponding to like components that are important. This failure is immediately displayed to you, and this makes it an overt failure. If your engine overheats, your temperature gauge tells you that. For covert failures, on the other hand, these are overt versus covert. So covert, you can think of like undercover. So that's typically what I think of when I hear covert. But these are things that just don't show themselves. These are things that are not obvious. So they're latent or hidden within the system. So this happens a lot for in-demand components, something that's not in use until you need it. So something that you don't turn on until absolutely you need it, and like something like a sprinkler system, for example. I think that's the example that Mattia uses. A sprinkler system does not turn on until you actually need it, and so these kind of components typically you go through a check cycle, or you go through some sort of you go through and you do a safety check and make sure it's on throughout the year so that when you do need it, it does work. And preventative maintenance minimizes the likelihood of a covert fail, but also of an overt failure as well. All right, so when you're going about troubleshooting, you want to do a couple things before you actually start putting your hands in stuff, and one of them is assessing the safety of the situation. So if something is not safe for you to start troubleshooting, then you really shouldn't start putting your hands on it. And there's a couple things that you want to take a look at prior to doing that. So this is listed as four basic failure direction from ATIA. And so when a component fails, basically it's designed so that it fails safely. The idea is that a system fails safely. However, there are certain things, certain elements within the component where a failure is not safe. So if we look down here, the four basic failure direction, fail safe would be okay. The system has failed, but I have in place some components where the failure does not lead to some cascade of events. Fail dangerous, on the other hand, does. So fail dangerous is when you have a failure and that leads to other failures in the component because the situation is dangerous. So there's fail known and fail unknown. I'm not totally sure what Mattia is getting at here. I'm with the I don't care thing. So fail known is something that you're informed with, like what the failure is. You know exactly what component failed or how it failed. The fail unknown is and he writes I don't fail I don't care. Mattia writes. I'm not totally sure what he means by this, but I'm going to treat this as a failure where you just don't know what happened. Something within the system has gone wrong. There is nothing monitoring that component that has gone wrong, so you don't know specifically what is going on. You're getting maybe an indicator from some other component that that component downstream is now starting to um, reach conditions in which failure may occur, you may be getting some indicator that something else within the system is basically acting awry, but you don't know what's going on, and so that's your job to kind of figure it out too as well. All right, so we're gonna look at an example. So Roman's having a rough day on the Beltline. Car broke down, and there's a bunch of like smoke or steam or something coming out of the hood. And so I go and I pop the hood, and then I decide to stand directly inside all of this smoke, just so I could, really smell and see what's going on. I'm just kidding. Don't do that. This I don't know why they're standing so close to the car, but right before the car started smoking and I pulled over, I saw that the temperature gauge in my car all of a sudden went from normal right here to increasing to getting very hot. So this is telling me that my engine is very hot. I open the hood, I stand inside of all the gas and smoke coming out of there, and now I basically, let's go about how these failures have presented themselves to me. I'm not a car guy. I'm not going to pretend to be a car guy. I'm an engineer, so if I'm given, enough information about something, I can do it physically. But if I were to open the hood of this car and it was acting like this, there's only a couple things I could do. So, all right. So overt failure was the smoke is an indicator. We're going to talk about how the different failure modes are occurring here and how they're presenting themselves. So overtly, I'm indicated, or I'm informed that there's a failure by seeing smoke coming out of the car. Also, while I was driving the car, I saw that the temperature gauge went up. This was a direct indication to me that some sort of failure is happening. Now, once I take it into the mechanic who actually knows what he's doing, he can investigate into what actually happened. And this is the covert failure of the system. So in this case, the coolant system failed. I wasn't getting coolant to where it needed to be. Something got very hot. And there's a few different reasons that could happen. The mechanic is going to logically troubleshoot this issue by going through these steps here. So is there coolant? The presence of the coolant. So if there is no coolant, of course the coolant system's not going to work. That's the very first thing he's going to check, or anybody who's going to check who's going to troubleshoot this manually. Then we're going to look at components. So, components that are a little easier to see, a little easier to test, hoses, adapters, and then eventually we'll look at bigger components, radiators, and pumps. Now, luckily for us, many modern cars have these components, all these major components, monitored such that they will inform the computer. Even if you don't see a readout, you can go to, AutoZone and they'll plug it in and they'll be able to see, okay, there's an error code here. Specifically, here's what's wrong with your car. All right. Next, we're going to talk about these actuated valves because these actuated valves are used in systems, and basically, when a system fails or when something fails, they go to one or the other state. It's either open or it's closed, on or off. So this is a pneumatic system. It's compressed air, and this can also be controlled with hydraulic systems, so like hydraulic fluid. And this is used in many, many, many technical applications. So the one on the left is called air to close, which means it requires compressed air. If you look on this doodle here, it takes compressed air, it fills this little chamber here, and it pushes the spring down. As it pushes the spring down, this plug goes into this orifice. Without the plug, fluid can move through here, through the orifice, and out the exit. However, when the plug is down, the fluid is trapped inside here and cannot move through the valve. Now, if this fails, if we have a failure in the control system, so the control is the compressed gas that actually, closes the valve. This is an air fail open valve. So if there's a failure in the control system, again, then this will just remain open. It is in its natural state, it's open. So this is important because if we're working with different components and there's a failure, we want the valve to be either open or closed. So the other one is obviously it's the opposite. So this is called an air to open, and also air fail close. So I need air to open it. In its normal state, you can see right here that the plug is in the orifice. I cannot like put fluid through here in its normal state. What I have to do is use a compressed air line or hydraulic line and actually actuate it by pushing the this little, like, I guess this little platform up against this spring. I push the spring up. That takes the plunger out of the orifice, and then like fluid is allowed to travel through the valve, and I open it. However, if the system fails, the control system fails, I have no compressed air, this valve will remain shut. It will not open until I actuate it. So this is an air fail closed, air to open valve. All right, and then so these are the failure states. We looked at a couple of these already. This is in your textbook. So there's a bunch of acronyms and stuff like that. We just talked about the first two. A fail last state. This is when a component doesn't move from the last state it failed. So you're operating something that's got a stepper motor, and there's a failure in the system. The stepper motor stops at wherever it is, and then when you start it back on, that's where the stepper motor picks back up. Now, fail last good state. So this is when basically you're able to take whatever the last good state, which means it was operating fine, and back up to that point. So for the stepper motor example, say I have a conveyor system that's operated with a stepper motor. I go back to wherever was a good point that I actually like communicated with another system. Hey, I'm here. And there's a few of these other ones. This first safe state. So basically, a first safe state is the program on the machine is restored. So this is like the boot up. So when you open up your laptop or your laptop dies, and you open it up and you turn it back on, it does one of two things, right? It either goes through its natural reboot process, and it brings up your iOS or your OS and your iOS or your Windows or your Linux. It brings that up and basically start fresh. This is the first safe state. Now, if you bring it up and it tries to restore all the windows that you were in, this failed last good state. So this basically tries to get you back to right before you hit failure. It brings up all your windows, brings up anything you were doing, brings up the 27 tabs you have open. This is called the fail last good state. All right, so then down here we have upscale slash downscale burnout. So basically this corresponds to when temperature sensors stop working. A de-energized state. So this is when something is de-energized. Basically, the electrical contact to it or electrical power that's supposed to be supplied to it is not, and we need to figure out why. Fail unknown. So Matthias seems to be joking here. Not totally sure why he's including this, but basically, this would be, if you had to categorize something and you went through it and you don't know yet, then everything is fail unknown until you can describe it with the rest of the states. All right, so then Mattia basically ends the chapter by referencing, okay, well these things are used in this system here, but then like shows the schematic, doesn't talk about it at all. I think this is a great opportunity for us to actually look at the schematic and see what we're looking at. So this system right here is designed to take hot oil and transfer heat to a cold fluid in order to heat up that cold fluid. So we're using the heat from the hot oil to heat up a cold fluid to a specific temperature. All right, so here's the system as a whole, and I've included a few more details so it's a little easier to read. So I have the hot oil in red and the cold fluid in blue. So the hot oil is coming in through here. It goes through this valve, assuming the valve's open, and it goes through this component here and out. Then I have the blue fluid, which circulates through here and basically is allowed to exit the system in this direction here. Now, what happens, like I said, is that they're exchanging heat. I'm using the hot oil to heat up this cold fluid to some degree. And how that works is basically in this device called a heat exchanger. It's adequately named. The two fluids exchange heat. And how they do this is there's a metal wall in between them. So a tube or you can think of a tube or even just a box with basically two layers. One fluid goes in one side, the other fluid goes in the other side. They don't mix. So the metal wall in between them, does not allow mixing, but does allow for the transfer of energy. So the hot fluid will heat up the metal, and then the cold fluid will absorb some of that heat. So it'll come out a little bit hotter than it was. The hot fluid will come out a little bit colder than it was. That's what a heat exchanger is. So then within this, we also have two separate types of kind of systems. We have this continuous flow system for the hot oil. So hot oil enters and leaves. It never accumulates. It's continuously flowing. It's there's no tank. It is a continuous flow system. And then a batch system for the cold fluid. So this right here represents a storage tank. So this accumulates fluid, and then after some amount of time or after some sort of event, it discharges the fluid in this direction here. All right, so speaking of the hot oil and the continuous flow system, how this is controlled, the flow of the oil is controlled using a flow control unit. And the flow control unit is this entire array of components here. The final boss, the one that actually makes the decisions, is the guy I got in this box line or this box dotted box here. But he takes information from these other components that are part of this flow control system. So let's break it down and see where he gets his information from. So he gets his information from two sources, this line here and this line here. This line here is a combination of a temperature measured by the cold side and some user input. Basically, the user decides, okay, I want the temperature and the temperature of the cold side and the temperature of the hot side to be this. I want basically my cold side to have, let's say it increases in temperature by 5 degrees. Okay. So I need to basically manipulate the flow rate of the oil so that I'm able to get that 5-degree difference in the cold side. Okay, so that's one source of information. Then there's also a temperature measurement here of the hot oil. And right here, the flow rate of the actual oil gets measured. So there's a device called a flow meter, and it tells me exactly how much fluid is flowing through this pipe. That is combined with the temperature of the fluid along with the information from the user input and the temperature of the cold side to decide to open or close this valve. Basically, should I add more hot oil or decrease the amount of hot oil? Do I need a further increase in temperature? Do I need more energy to dump to the liquid side? Or am I dumping too much? I need to dial it down. So then the cold side is kind of similar, but kind of in reverse almost. So and it's also a batch system, we said. So the flow goes through, it circulates through the heat exchanger, and then once it reaches a certain point, it discharges through there. Well, this has the way it discharges is basically it has this system here, and the system here is a float switch or a level switch actuated system. So basically, inside this tank, there's a little switch, and a little switch is made out of some material that's less dense than the liquid. So it's got two states. It's got a state where it's basically like it's hanging. There's a joint or something like that typically, and there's no liquid. So as the liquid rises, like I said, the material is less dense. The liquid rises and it pushes the switch up, and then now it's in its second state. So this is typically its on state. So off as the fluid's here, on as the fluid's here. This tells us, okay, once I've reached this point, hey, fluid's up to this level. It tells the controller opens the valve and discharges the fluid. Now, if you have an array of those, you can have it tell discharge the fluid until it reaches the second one. So it looks like we have two here. So once the liquid reaches this level, I open up the valve, and I discharge fluid, and I discharge fluid until the liquid level comes back down here. Then I close the valve and I continue the process. And this, remember, this jagged line is just basically there's something else that we're not included in the schematic, but that is indeed a part of the system. That's going to be where the source of this cold liquid comes from. Okay, so this is more information than you need, I know, but this is also something cool to look at. So this is an application. This is something we're talking about is a direct application, and it's nice to get exposed to these engineering schematics. But the big thing that really Mattia was trying to use is that each of these has a fail closed control valve. So both of those valves are designed so that if I cannot actuate them, they close. And this is good. This is very good for systems where you have, some fluid running through them or, hot air or whatever. You want a failure for valves to close because then that fluid or that hot air or that hot oil cannot just continue through the system. If there's a failure downstream where there's a rupture or a leak, you don't want to continuously be sending fluid in that direction. So both of these valves are fail closed valves. All right, so then this is just some of the on the schematic. The schematic has a bunch of like tags for all of the components. We're not given any of the information on the components. You don't need to know this, but again, I thought this was cool, and it's good exposure to have. So I just wanted to show a couple of like the tags, what they do, how they're named, basically some of the like standard procedure when it comes to these engineering schematics. So they are labeled with somewhat intelligent names. The um, the F the three Fs here, that excluding the FC, but the three top Fs here are part of that flow control system. So they all basically decide how much hot oil gets sent through that heat exchanger. FC, we saw that's the two valves. Those are both fail closed valves. The TDT, this is an array as temperature detector transmitter. It's hard to say, but this is an array of RTDs, which are resistive temperature resistance temperature devices. And they basically, what happens is it's a device where the electrical resistance changes depending on the temperature. If I have an increase in temperature and I run current through it, then basically I can measure, okay, there's a change in the resistance of that material, and that's associated with the temperature. Again, more than you need to know, but it's kind of something cool. This L right here, LT and LIC, this was part of our float switch system. So this is the float switch itself, and then the controller that informs the valve, hey, open or close based on the level of liquid in the tank. All right, so just to summarize everything we've done for this chapter, we looked at covert and overt failures, how different types of mechanical failures present themselves. We looked at different states. So is it when it fails, is it fail so it's always open, always closed, always on, always off, really? And then failure direction. So basically, how to approach troubleshooting in a safe way. And then we also gave you a little bit of intro to looking at engineering schematics. So again, that's information that you don't really need for this class, but you can take away and use it. And it also makes it more interesting to learn this material when we can see it's directly applied.